Testing. Hello? Okay, testing, great. There we go, yeah. How's that volume? Okay, yeah, that's all right. And got just a minute left, so I'm just, okay, pretty full up still. And yeah, we're probably maybe 30 seconds early, so I'll just go ahead and start. Quick housekeeping before we get to that. P, if and only if Q. Someone asked me about this yesterday, or the last class, and I didn't get to it, so I just want to get to it. This is two statements, really. You're going to see it on your homework. You have probably seen it on your homework already. It's P implies Q, and Q implies P. So if you have to prove an if and only if statement, I usually break it up, and I say proof, and I do a forward direction, and I do a backwards direction. And then I just have, a proof here and a proof here. So just P implies Q is a really powerful statement, actually. It's saying that they're basically equivalent. Anytime P is true, Q is true, and vice versa. They're kind of a way of relating two propositions that is a really strong bond. And yeah, it's two individual proofs. So, for this one, you want to imply Q implies P, but maybe you prove it by contrapositive. Maybe it's not so direct as you just assume Q, show P, such and such. So treat it as two separate proofs. That's really only the housekeeping I wanted to say on that. Any questions about if and only if, and then we'll just kind of jump in. Okay, great. Warm up. What is 1 plus 3 plus 5 plus 7 plus all the odds up to 99? This is kind of like a cold question. If you haven't seen it, it might be a little tricky, but adding up all the odds up to 99, what is that? Who thinks they might have an answer for that? Okay, a few people. The people that think they have an answer for it, did you use Gauss's method? Keep your hands up. Okay. Yeah, so we're not going to do it that way. If you've seen how Gauss adds numbers like that, ooh, thank you. Magic. All right. So yeah, adding up the odd numbers, 1 through 99. We're not going to do it through Gauss's method. We'll see what that is later. But we're going to try something different here. And I'm not going to send you into pairs for this. But what I'm going to say is start with small examples. This is a fundamental principle, or skill, really, of a mathematician. Is anytime you look at something and it seems hard, start small. So just for a minute, just go pencil and paper or iPad or what have you. Try to see if you can get a sense of what this might look like, what the answer to this might look like by starting small. So I'll just let you do that for a moment. Okay, starting small, who sees a pattern? Okay, more and more hands are coming, great. Great, so as you start small, let's see a pattern. And the big question is, what does start small mean? Like, if I didn't have that up there right then, what does start small even mean? I just gave you a single question. You need to create a small version of that. What does that mean? Any thoughts there? Yeah.
Instead of trying to add all the numbers at once, add the first few numbers.
Yeah, we're adding odd numbers. I just keep losing the markers. We're adding odd numbers. So let's try adding less odd numbers. If we start with 1 plus 3, simple, 4. Okay, nothing to see there yet. We just saw 1 plus 3 is equal to 4. 1 plus 3. The next odd number, 5. 4 plus 5 is 9. If you're really looking for a pattern, you might see it. But still, it's only 2. Seen too much there. plus 5 plus 7. 9 plus 7, we got 16. Who sees a pattern here? Yeah. So 4 is a perfect square. 9 is a perfect square, 3 squared. And 16 is a perfect squared. So let's try one more, just to see if our intuition is correct. 5 plus 7 plus 9. 16 plus 9 is 25. Perfect, which is 5 squared. And if we really want to be sure, always start small. Great. We're happy. So we want to make a conjecture now. Adding up all the numbers up to 99 might seem a little bit daunting if you're trying to do that by hand. But now we're seeing a pattern. So there might be more structure to this than we originally thought. So can someone make a conjecture here? Just in natural language, not anything formal yet. Just start with a conjecture. Yeah?
Adding n odd numbers, their sum will be n squared.
So in plain English, adding, how's that marker? Is that getting too dry? All right. Let me know if this is getting too dry. I can move to a different color. Adding the first n odd numbers is equal to n squared. All right. So now we're getting pretty used to things. We want to write this as formal language. Ooh, what's happening here? You're fine. So adding the first n odd numbers is n squared. This is a conjecture. We haven't proved it yet, but we've started to just make, let me write that bigger, conjecture. And one thing I really want to be careful to do for all the people watching at home is to not write between boards. I kept forgetting that last time. OK, so adding the first n odd numbers is going to be n squared. That's our conjecture. So what does that actually mean? We have 1 plus 3 plus 5 plus dot, 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 all the way to, well, it depends on how we define odd. We could do 2n plus 1 minus 1. Which one do we want? So plus 1, we've been using that a lot. We could use minus 1. We could use plus 3. We could use a lot of things. But let's just check our intuition here, or our sanity. Just do a sanity check. So for, let's say, n equals 2, we have 1 plus 2 times 2. And then we want to see add or minus. So if we do minus, that'd be 4 minus 1 is equal to 3. OK, so it seems like we want minus here. You know, we could always try it out for another. But we just want to be clear about our definition. Otherwise, we'll have off by 1. We have to put n plus 1 squared, what have you. So again, a big part of math is getting the right definition that helps us do the proof. If you came up with a different definition, you do a proof. You would just have n minus 1 or n plus 1 or whatever here to make it be true. OK, so we have 1 plus 3 all the way up to 2n minus 1. We're not going to use this too much, but it's good to see once. And here's a good class to see it. Who's seen this notation before? OK, that's most of you. If you're taking calculus, which is a prereq for this, you've probably seen it. It's a summation. This goes, in our case, from n equals 1 to, no, we want that I equals 1 to n. And I didn't even write what the definition was. OK. So 2I minus 1 is equal to 1 plus 3. There we go. All right. So if you haven't seen this before, and you're a computer scientist, which is why you're in the computer science class, this is basically just a for loop. Start I equals 1, and then you just increment it by 1 each time until you get to n. And each time you're just adding. So this is a summation notation. If you had something like this, that'd be product notation. So you multiply them together. We won't use these too much, but it's good to see them. Great. So conjecture. What's our conjecture in formal language? We're getting pretty good at that now. We could say for all n in the naturals, well, we're starting with 1, so plus, don't forget, not 0 doesn't work for what we're doing right now. 1 plus 3 plus 5 plus all the way to 2n minus 1 is equal to n squared. Great. So we have a conjecture now. We haven't proved anything yet, but we have a conjecture. And I'm just going to draw something right here. So I'm going to draw a square. Bum, bum, bum. Yeah, let's do that square. So this is a 3 by 3 square. By 3. That means there's 3 squared points, 9. And I'm going to ask a question with very little to give you, just to think. Apparently, this is 1 plus 3 plus 5. That's what our claim is. 1 plus 3 plus 5 is equal to 3 squared. And my question is, if I wanted to add 7, let me write bigger, plus 7, and I want that to be 4 squared, on this picture, can you picture where I can add 7 to make this be a 4 by 4 square? Where can I add 7 points to make this a 4 by 4 square? So letting people think for a moment. Yeah. Got this right here. Here's 7 points. And now we have a 4 by 4 square. Who can picture where if I wanted 9 to get a 5 by 5 square now? We have 1 plus 3 plus 5. And we have our plus 9 here. So it's pretty convincing, right? Like it feels like if we add 11, if we add 13, we can just keep going, and we'll get this picture kind of shows us why when we add odd numbers, we get perfect squares, and we can just kind of keep that going. This is a proof by pictures. I love proof by pictures. They make everything click right. But it's not the type of proof we're doing in this class, so we're going to have to make this formal. This gives us intuition for where to start. So when you're proving things, math, we have, all these proof techniques. We have direct, contrapositive, contradiction, cases. We have all these De Morgan's rules and logical equivalences. It seems like a lot of it is plug and play, where you just kind of like go through the steps. But there's a lot of creativity in math as well, right? There's a lot of things where you have to search for the answer, set up the right definition, draw a picture first, and then turn it into something formal. So whenever you get a chance, draw pictures. That's not the final proof you write in the homework, but if you can get a good picture, that can help lead you to a proof. So let's actually try to prove this a little bit. Because, all the proof techniques we've done so far, if I tried to have you prove this, well, it wouldn't be direct, and it wouldn't be contrapositive. Can someone tell me why direct or contrapositive isn't so relevant for this one? Yeah. Mm-hmm.
You don't have a if or a...
Yeah. These are really set up for P implies Q types of proofs. Both of these, they're set up for implication. So direct and contrapositive doesn't work. We could try contradiction, but that kind of sets us up at a bad place. Like, again, so much of when we want to write a proof is we want to get our hands on something. Get our hands on a definition, and then you can just rewrite the definition until helpful stuff falls out. But if we put a not in front of here, well, then we lose, we lose kind of a nice thing to have our hands on. So you could try contradiction. I wouldn't. Wouldn't be my first try. Again, we could try cases, maybe. But what we're going to do is we're going to introduce a whole new mystery proof technique. This will be our last one. So, so far, what we've covered in class, we've had 2 lectures, and they've been pretty blazing fast. We introduced all the propositional logic and all the proof techniques, except one so far. If you've done proofs before, that may feel doable. Otherwise, you're learning a whole new language very fast. So I'm just going to let you know right now, this is the last proof technique, and then you'll have all the proof techniques that I have. In my mathematical career, all these proofs, yeah. Thank you, amazing. Better marker, great. So we're going to have all the proof techniques that I have, and the rest of the class is going to be a bunch of applications of math to computer science and a bunch of proofs about specific types of mathematical objects. But we'll have our entire toolkit. So if you felt like it's moved a little bit fast, the toolkit we are using now, we're going to use it for the rest of the class. So you'll get a lot of practice practicing that new language, this formal language that we're learning. So let's go ahead and learn the last proof technique that we haven't touched yet. So yeah, it's not clear how to prove this. That's the problem. There seems to be some intuition that, like, well, when you have a square, you can add an odd number and get another square. So let's go ahead and see if we can do that at least. Let's say we have n squared and add, what do we have, 2n minus 1? Right. Or actually, no, here's the deal, right? We have n squared filling out 1 square, and now we want to add another odd number, the next odd number, which is 2n plus 1 minus 1. Does this make sense? We're kind of going to the next odd number. We're just incrementing it 1. It's still 2n minus 1, except now our n is n plus 1. We're going to the next one to add the next L shape here, right? The n plus 1th L shape. And hopefully, this should be a new square as well. And let's just kind of give it a quick check. 2n plus 2 minus 1, which means that's n squared plus 2n plus 1. Is that a perfect square? Yeah, we can write it as n plus 1 times n plus 1. If you did that foiling out, we get an n squared, we get 2 n's, and we get a 1. OK, so it seems pretty good. We start with a square, we add a new odd number, we get a bigger square. That is, in this case, n plus 1 squared. Great. Who feels this proof isn't as solid as the proofs we've been dealing with so far? There's a lot of intuition here, right? There's a lot of intuition. We've gotten our adding up the odd numbers. We see the picture of the squares. We can see when we have a square and added the next odd number, we get a new square. But there's nothing formal here. So let's write it over here. No, over here. All right. So we have our formal conjecture. We have our picture. Perfect. We're going to create a new proof, or the last proof technique. It is called proof by induction. And this is going to give some structure to what we were just trying to prove there. And it's going to look a little bit jargony and a bit gnarly. And then we're going to make that feel a little bit less jargony and a little less gnarly. So first off, whenever you want to prove something by induction, it's because you have a conjecture that you want proved. And your conjecture is always going to look like this. Something like this. For all n, p of n. Can someone remind me what this is? It's like a proposition, but it depends on a variable. Yeah.
Predicate.
Yeah, right. So this is a predicate on n. This is just saying that something holds for every natural number. Okay? And the way we prove something like this is 3 steps. Again, these are going to be a bit jargon before we look at it with an example. We prove a base case that is show P of 0 is true. Okay. There's something called an inductive hypothesis. And this one is going to be a little bit weird until we play with it a bit. But it says, let k be in the natural numbers, and then we just assume that p at k is true. And then we have one last one. Before we get there, this is kind of a weird thing. Inductive hypothesis. We're assuming that p of k is true. Who's a little bit bothered by that? We're kind of assuming what we want to prove, right? We want to show p is true for every n, and now we're just going to say, let k be a natural number. We're going to assume it's true. Okay. So it's a little bit of a weird structure, but let's finish it off. The very last thing is called the inductive step. And that is show p of k plus 1 is true. Okay. Like I said, a bit jargony, a bit formal, and a bit abstract. Who would appreciate an example to kind of see this be put in context? Okay, yeah, quite a lot of folks. Good thing we have an example. We were playing with one just a moment ago. So let's see if we can prove this conjecture, that adding up all the first n odd numbers gives us n squared with this structure. Okay. So again, what's our conjecture? Well, this is our conjecture. We're saying for all n in the naturals, the positive naturals for us, and then we're saying p of n, where p of n is equal to this, right? P of n is this equality. P of n says that adding up those first n numbers gives us n squared. That's our predicate. Does this equality hold for all n? So let's just step through and see what we do. Base case. This is going to be our proof. Base case. So this is a little bit weird. We want to show that p of 0 is true. Can someone tell me what's wrong with p of 0 being true? Like, why that's not so relevant for this specific problem? Yeah.
Because we're not really dealing with cases where we have 0 odd numbers, although I guess if you did 0 is a square, so you would have 0 equals 0 squared.
Right. We're not dealing with 0 specifically. Like, we look in our...
Also 0 is not possible.
Yeah. We have our conjecture right here. Well, right here, actually. This is our conjecture. And it says for every positive natural number. So we're just... This is a little bit of a lie, you know. We don't have to do this all the time. Doesn't have to be 0. So that's just a little caveat. This is generally the structure, but you know, it doesn't have to be 0. What we're going to start at is p of 1. Right. We want to show p of 1 is true. Well, what's p of 1? This says that 1 is equal to 1 squared. That's really all it says, right? Add up the first odd number, and you get a perfect square. The first odd number just adds to itself. There's nothing to add it to. So there's the first odd number. It's equal to 1 squared. Done. So we've checked off the base case. Still not showing lightning, but let's keep going. Inductive hypothesis. You get tired of writing it at some point, so I usually write that. Ind hype. So we have our inductive hypothesis, which says let k be in the natural numbers For us, it's going to be plus because we're not dealing with 0. And assume that 1 plus 2 plus, or not 2, 1 plus 3 plus 5 plus all the way up to 2k minus 1 is equal to k squared. We're just kind of assuming what we want to prove. The step there, you don't really do anything. All you write out is what you're assuming. And then lastly, we want to do the inductive step. And right now, we're just kind of suspending disbelief for just a moment, right? Because we don't know why this is going to help us. We haven't talked about why it's going to help us. But the inductive step says, OK, what about k plus 1? What about k plus 1? So now I have 1 plus 3 plus 5 plus all the way to 2k minus 1. And we're adding one more. We're adding one more odd. That's the k plus 1 place. And it's 2 times k plus 1. Sorry. K plus 1 minus 1. Right? We're just incrementing that odd number 1 by 1. OK, so I just wrote out that sum. What I'm trying to show is that p of k plus 1 is true. That is, this should be k plus 1 squared. So we can write it out again. What we want to show is that this is equal to k squared. I'll actually want to show this is k plus 1 squared. So how can I do that? I have all of these numbers. Can someone see a k squared in this sum? Yeah. So here's the trick. Here's the whole trick of proof by induction. These numbers here, those have to be k squared. Why? Because we assumed it. We don't know about this k plus 1, but we do know these are k squared. Right? We can say that, I'm going to rewrite this down here because it's not so pretty. What I'm going to say is 1 plus 3 plus all the way to 2k minus 1. And then we have the rest of it, 2 of k minus 1 plus 1. This part must be k squared. And we can just write by inductive hypothesis. And if that's k squared, then we have it's equal to k squared plus that, which is, let's factor this out. This part is going to be is going to be 2k, what we wrote over there, 2k minus 2 plus 1, which is equal to 2k minus 1. That might be getting a little small, but what we're doing is just what we did right here, right? We have basically an n squared, and then we factor this out, and we get n squared plus 2n plus 1, except we have k here. Yeah?
I think there's a mistake. It's not 2 times k minus 1 plus 1. It's 2 times k plus 1
2 times k plus 1 minus 1. Thank you.
And then that would make it 2k plus 1.
Mm-hmm.
So we already have it.
Thank you. Yep, that should be a k plus 1 in there, and that should be a minus 1 right there. We had it right up here, but not right there. Thank you. So that's 2k plus 2 minus 1, which is equal to 2k plus 1. Great. So the main point is, at the very end, we just do this proof at the end. Right? We can just show that this is k squared plus 2k plus 1, which is equal to k plus 1 quantity squared. what proof by induction says is we're done. It's a little bit weird because, like, what did we just show, right? What did we just show? And really, we just took this inspiration and we just made it formal, right? It says, anytime you have a square, you can add the next odd number and you get a new square. So, yeah, we're going to have to sit with this one for a moment. I'm going to have you prove something, and I think that'll help think about it some. But really, what proof by induction is doing is all we did with that picture there, which is to say, if it's true somewhere, it's going to keep being true. Right? So this kind of sets up a domino effect, or proof by induction sets up a domino effect. It says, I can't write past that board. Okay. So what it says is if you have a domino here, call it P0, and then you have another domino, P of 1, and so on, P of K, and P of K plus 1. It says, and there's dot, dot, dot there, the inductive hypothesis and inductive step says anytime you knock a domino over, the next one will follow. The next domino follows, and forever on after. So what this picture shows us is that if we have a square at any point, we can add an odd number and get a new square from it. And then we have a square there. You can add an odd number and get a new square from there. So proof by induction is kind of this little sleight of hand. It's this little magic trick. Yeah? We will, yeah. So the question was, when does it break? If you have a false assumption, can you show something that looks correct but isn't? We'll show an example of that in just a little bit. But yes, this base case is so important because it kicks off the good dominoes, right? It says when you start something that's true, the inductive hypothesis lets you show that it'll keep being true. So I think rather than talking more, I'm just going to give another proof and or another problem and let you all prove it. So take a moment to introduce yourself to a neighbor if you don't know them already, and I'm just going to write up a new problem. Clap once if you can hear me. Clap twice if you can hear me. Clap 3 times if you can hear me. So I'm just going to have you work in the pairs you just made on proving this by induction. And real quick, before you do that, just turn to the person on the other side of you that isn't the person you're partnering up with and make sure that they have a partner. If they don't, then you're just a 3-person team. Go ahead and just work on this. I'll walk around, and then we'll come back to the board. And in case it wasn't clear, this is divides. 3 divides n cubed plus 2n. All right, let's just take a very quick start. Let's take a very quick look at just the beginning. I'll let you go back to your group. If you're still working, I'll let you keep working. But we're just going to take a quick look at the very first thing. So the very first thing for a proof by induction is, of course, the base case. And in this case, we're showing it for every natural number, not just at 1. So we're trying to show p of 0 is true. First off, what's p? What's our predicate here? Yeah, so our predicate is just this statement. 3 divides n cubed plus 2n. So if we're plugging in p as 0 there, 3 should divide 0 cubed plus 2 to the 0. So divides is not an operation here, right? We're not saying 3, we're not actually dividing anything by 3. It's a proposition. It says 3 divides something. What does that mean? Can someone tell me again the definition of divides? Yeah.
If you have a divides b, it means that b is equal to some integer times a.
Yeah. So if this divides that, there should exist a k in the integers such that 3 is equal to this side, which, what is this side? 0 cubed plus 2, 0, that's just 0. Right? So 3 is equal to k times 0. Oh, did I write that right? There exists a k such that 0 is equal to 3 times k. Oops. Which is to say, again, so A divides B is the same thing in English as B is a multiple of A. Right? So if A divides B, B is a multiple of A. We want to find a k. There exists a k such that B is equal to k times A. So that's what we have here. 0 is equal to 3 times k. What k works for this? 0, right? So k equals 0 makes this work. Great. OK, so that's our base case. We're just showing that for n equals 0, this statement holds at least there. OK. Next thing we have to do is make an inductive hypothesis, which is you just write this down. There's really nothing more to do with the inductive hypothesis than just write down. Can I erase this? Yeah. Yeah, we've proved all this. Great. And then I'll send you back into groups after we write this down. The inductive hypothesis, again, is just that let k be in the naturals. Assume that 3 divides k cubed plus 2k. And what do we want to show? Yeah. So now we just want to show that this same thing holds when we plug k plus 1 in. We're assuming this is true, and we want to show that if we put k plus 1 in there, it's going to keep being true. So induction takes a little bit to work through. I'll let you go back into groups now. I just want to get us all on the same page with base case. one thing I forgot to give you that you might find helpful is a squared AB. So you don't need to stop working. I'm just going to let you know this fact. If you find this useful, you don't want to write out, there might be a lot of multiplication you have to do. This is a fact. Keep on working, I'll be around. Perfect. Okay. Great. How are things going over here?
Are we doing this one though? Like, or like?
What's that?
Wait, are we
Oh, no,
still
that.
doing
Yeah, we're still doing the same one.
Oh,
Mhm.
okay.
Okay, yeah, it looks like
Yeah,
you're
we're
pretty
on-
far. Great,
yeah.
great, perfect. Okay. Okay, everybody. Yeah, this is back on. Okay, so we're going to start back up there. Take up the last few minutes writing down your last thoughts. I'm seeing a lot of progress here. Okay. Clap once if you can hear me. Twice if you can hear me. Hey, everybody. I was walking around quite a bit, and it seemed like there was a lot of productive thoughts here. So we've shown the base case together already. We needed to remember what A divides B means. That's really helpful to us. And then we just kind of did this magic trick where we just said, assume that it's true for K. So the inductive step, can someone tell me what they did to start the inductive step? Just the very start. Yeah.
Plug in P of 0 and get 3
Right. So we're just going to plug in K plus 1. We assume that it's true for K, and now we want to see what about K plus 1. So K plus 1 cubed plus 2K plus 1. Is that visible? Yeah, okay. So again, this is just this side right here, and I plug K plus 1 into K. So I forgot to give this to you earlier. This would have been nicer to start with, so you didn't have to do multiplication cubically. But if we knew this is true, then K plus 1 cubed is going to be equal to that. Let's see, we get K cubed plus 3K squared plus 3K plus, okay, so that's just one thing. Oh, no, we have a 1. And if I did any of the multiplication wrong, someone please catch me. Plus 2 times K plus 1. So all we did there was we plugged in K, and we started multiplying things out. I'm going to erase this now. And I'm going to move up here. So let's just group terms. Right? So right here we have what? We have 2K plus 2. And then we can group terms. We have K cubed alone. We have 3K squared also alone. We've got 3K plus 2K, so that's 5K. And then lastly, we've got 1 plus 2, which is 3. Great. All right, who got that far? Great, perfect. Where'd you go from there? Yeah. Mm-hmm. Great. So we're using the case of P of K. So what we really want to find is a k cubed plus 2k within this. Because if we have k cubed plus 2k, we know it's a multiple of 3. Right? So where's a k cubed plus 2k? Well, here's a k cubed. And if I take off 2k from here, then what I have left over is 3k squared plus, well, I took off 2k from this, so that's 3k, plus 3. Good. And this is special, right? Because we assume that it's a multiple of 3. So now, by definition of divides, 3 divides k cubed plus 2k means that this is a multiple of 3. That means there exists j such that k cubed plus 2k is equal to 3j. Right. That's the inductive hypothesis, and we write by inductive hypothesis. That's part of our proof. And then lastly, what this turns into is 3j plus 3, well, here's the trick, right? We can just factor all those 3's out. Not too hard at this point. K squared plus 3, or no 3, plus k plus 1. Lastly, factor that 3 out one more time. And now we got 3 times j plus k squared plus k plus 1. Can someone tell me why we're done? Yeah. Mm-hmm. Mm-hmm. So on this high level, we're done because we finished the inductive step. And since the base case is true, we just kind of propagate through. But like this last step right here, we're also done because this, that's too cramped. I'm just going to erase this. This is an element of z, right? We just have a bunch of integers that we're multiplying and adding, so that's also in z, which means the whole thing is a multiple of 3. Right? We could call this k prime if you want. Now I have 3 times k prime in the integers. Yeah?
You don't have to define the values of j, can they? In the there exists j such that.
So yeah, this is the neat part. We don't need to know what j is. We don't need to define what j is. All we need to show is that once we plug k plus 1 in here, we're going to get a multiple of 3. And because we know that by inductive hypothesis that this is a multiple of 3, we just know there exists some j that makes this a multiple of 3. We don't need to know what it is. Yeah?
Wait, do you have to specify the universe that j is in, like integers or something?
Yeah, I should have done that. Thanks. So let's make this, there exists j in z. Yeah?
Wait, isn't it natural numbers? Because the inductive hypothesis let k be part of it.
Mm-hmm. So what we're proving is that it's going to be true for every natural number. We're just looking at what the definition of divides means. So we're not doing p of j anywhere. We're just saying that there's some integer such that 3 times that integer is equal to this. It's probably going to be part of the naturals. If 3 divides all of these, yeah, these are all going to be positive if we're talking about the naturals. So it's going to be a natural number. If we wanted to strengthen it, we could make this a natural number. We might have to do a little bit extra to prove that it will be a natural number. But right now, all we're saying is that 3 is a multiple of k cubed plus 2k. Okay. So again, hopefully it feels a little better to have worked through this yourself and to see that, like, okay, what does it mean to show a base case, do inductive hypothesis, do the inductive step? But there's still this kind of thing of why does this work? Are we not just assuming what we want to prove? So last thing we're going to do, or not last thing, but what we're going to do now is I'll show you real quick, or we'll look at real quick, like what was asked earlier, which is, does this break ever? Does this ever, can we ever fool ourselves and actually break something? So I'm going to prove to you. Does anyone still need this up? Yeah. Mm-hmm. In the integer. Mm-hmm. No, we're typically proving things for the natural numbers. Mm-hmm. So here's the distinction. The question was, for inductive hypothesis, should we be doing it for k in the integers instead of just the natural numbers? Why not start proving things over the integers writ large, especially if we're dealing with this definition of divides? Where here's the definition of divides, which I guess I didn't put it here either, but there exists k in the integers. That's the definition of divides. A divides b, that is, b is a multiple of a, if there's some integer where b is a times k. So we're dealing with the integers, but that's not what we're claiming to prove. What we're claiming to prove is that for every natural number, let's see, does it work for, let's plug in -1. That'd be -1 minus 2. I don't think that works for -1. So let's see. -1 cubed plus 2 times -1, that's going to be equal to -1 minus 2. Oh, it kind of works. OK. Maybe you could prove it for more things. Does it work if you get to -2 in this? Oh, OK, we're not going to worry about that. So it might work for over the integers, but the claim that we're trying to prove right here is that it works for every natural number. And the way we make it work for every natural number is by setting up these dominoes, right? Those are thick dominoes, but that's fine. And we start at p of 0. So if we try to prove it for the integers, it'd be a little bit tricky because we would need to knock the domino forward and backwards. We would need to set that up a little carefully. But the main point is if we assume it for k, p of k, inductive step says we can move forward. That p of k gives us p of k plus 1. And p of k plus 1 gives us p of k plus 2. And so on. And then p of 0 is the first domino that knocks everything over. Yeah? Oh, OK. Yeah.
Would that be kind of like that where you, if you have the integer and you just prove it forward,
Ooh. So the question was, if we do it forwards and backwards for all of the integers, is that like an if and only if relationship? I don't see an if and only if in there, like a statement where the if and only if connective comes up. But it is kind of like if and only if in that you might, one way to prove it is to make two proofs, where you prove going forward, and then you flip it around and say going backwards as well. That p of k shows pk minus 1. That's not typical. You could try it. Yeah. Is there a hand over there?
yeah, I was wondering, could you also apply this for a continuous function if instead of plus 1, you just had some infinitesimally small variable, or had some variable and did the limit as it approaches 0 or something?
Ooh, that's getting real tricky. So the question is, what about like the real numbers? What if we try to prove something instead of just the natural numbers? No, this is why we're in discrete math. Right? We're dealing with the natural numbers. We're dealing with the counting numbers. It's a different flavor of math, too. If you do real analysis, if you do continuous mathematics, you can prove some things by induction, but a lot of the math you'll do has a different flavor. And discrete math really has its own flavor in a lot of ways. Induction is one of the strongest signatures of discrete math. Right? That's really kind of one of its calling cards. So I'm going to prove to you something that I shouldn't prove. And let's see. So conjecture. And it is for all n in the naturals. 8n plus 3 is even. Shouldn't be true. Plug in 0. Plug in 0, we get 3. Shouldn't be true. But I'm going to prove to you that it is. So first off, we start off with our inductive hypothesis. which is for all k, not for all k. We're going to say let k be in the naturals. Assume 8k, plus 3 is even. And now I'm going to show the inductive step. So again, the inductive hypothesis, there's not much to it. You just assume what you're trying to prove, and then you show it for k plus 1. Inductive step is let's look at a times k plus 1 plus 3. Well, I can factor the 8 through. We get 8k plus 8 plus 3. Well, that gives me 8k plus 3 plus 8. I just kind of regroup things. Inductive hypothesis, 8k plus 3 is even. So that means there exists j in the integers such that this is equal to 2j, which implies we have 2j plus 8. And I can factor 2 out. Well, let's just factor that 2 out. 2j plus 4. And let's not get on that line. Great. OK, so now I've just shown that we assume our inductive hypothesis. Now I plug k plus 1 in, and I get 2 times j plus 4, where these are both in integers, so this is an integer as well. So what went wrong? How did I just prove that these are all evens? Yeah? Yeah, we didn't do the base case. And what that says is that you can set up your dominoes. What I did, I proved a thing. I did prove a thing. I proved that if 8k plus 3 is even, then 8 times k plus 1 plus 3 is even. Yeah? It doesn't show up there. OK, thank you. Great. So let me prove this false thing a little more visibly. Great. So where did we leave off? There exists j such a great, right? OK. So that implies 2j plus 8 is equal, or really it's equal, is equal to 2j plus 8, which is equal to 2 times j plus 4. Great. And this is in the integers. So this proof does prove a thing. It shows that if you have a domino here, the next one will fall. And that happens forever. But you could prove things that have no beginning point. That is, this is never true. There's never a base case that kicks off the rest of the dominoes. Right. So this is a problem, right? Or it's not a problem, it's a danger. You can think you proved an infinite amount of things and actually have proved nothing. And this is kind of like, what it's saying. It's not saying exactly this, but if you think 3 is an even number, and we know the definition is 2k plus 1 for an odd number, or we know that odd numbers jump. If 3 is an even number, then so is 5, then so is 7, then so is 9, then so is 11. Right? The problem is if you start with something false, you can keep getting something false. And that's kind of true everywhere. If you start with a false assumption, you can get anything. Bertrand Russell, a famous mathematician in the 1900s, working with a lot of kind of the foundations of mathematics, trying to show what's true and not. There's a famous story about him where he was at a press conference and was telling the press that if you start with a false assumption, you could prove anything. And this is kind of dangerous for the press because they're like, oh yeah? Well, show that you're God. And he was like, well, OK, well, if 0 equals 1, then 1 equals 2. And God and I are 2 separate beings. But if 2 equals 1, then we're actually 1 and the same. So, it's a little glib proof. But the point is, we know this. We know P implies Q. If you start with false, you have vacuously true. If you start with false, you could prove anything. false implies false. You can keep getting whatever you want out of it. So be real careful with induction. The base case is crucial. Yeah?
What happens if you run, when you do the inductive step, you run into a contradiction, or it's like you don't know where to go next? Does that mean like the original proposition is false?
So yeah. The question is, and let me make sure I'm getting the question right, is let's say you have a base case. Let's say you have your inductive hypothesis, but you're having trouble getting the inductive step.
Or let's just say in the inductive step, you run into a contradiction.
Okay. You're saying run into a contradiction. So you assume P of k is true, and you're trying to show P of k plus 1 is true. If you run into a true contradiction,
Could that ever happen? I'm just like hypothetically thinking about it.
could that ever happen? I think it could happen. So let's see. You're assuming P of k is true, and then you hit a contradiction. You might be contradicting the fact that P of k is true. So I don't know of an example offhand, but you might be showing that there at least exists a k where P of k is true. Yeah? Mm-hmm. Yeah, sometimes there are cases where you have more than one base case. We're not going to be dealing with those so much in this class. But yeah, sometimes you need more than one base case. You've seen those dominoes like on social media where it does a whole fancy thing, right? You have like this line of dominoes that you kick off and this line of dominoes, and then they converge and like knock a thing over that like shows Mario's face or something, like. Sometimes you have multiple base cases, and you need to kick them both off, and then they kind of let everything go out. So you can sometimes have multiple base cases. So yeah, you can certainly have trouble proving this, especially if it's a false thing. It's hard to prove false things. But one thing I want to say is what this is saying is that for all n in the natural numbers, P of n is equivalent to what this is saying, which is P of 0 and, let's see, for all k in the naturals. Can you see that far down up there? Great. P of k implies P of k plus 1. So what this is saying is these are equivalent. If you want to show this, you can show this and vice versa. And the reason this works is because this sets up the dominoes. It says if you can show that every time P of k is true, sets off P of k plus 1, you have this dominoes set up, and P of 0 kicks it off. Yeah, so this says if you kick off the dominoes and they're all set up properly, you get it for every single n in the naturals. 10 minutes, great. Let's do one last proof in our 10 minutes. Yeah, we're going to strengthen this is what we're going to do. Any questions? Yeah. No, there's no perfect proof technique. In fact, real quick, the Gauss method, we're going to do 3 plus n. So this isn't all the odd numbers. This is just adding up the numbers 1 through n. You could prove this by induction is equal to n times n plus 1 over 2. Right? So this is something you'd prove in the notes. It's proved by induction. You can prove this by induction. There's this famous story of Gauss. I guess I'm telling stories today. Gauss, the story was that he was in elementary school, and his teacher was fed up with him. So he said, OK, Gauss is being asking too many questions. Let me tell him to add up the numbers 1 through 100, and that'll keep him busy. And then just a few moments later, he was like, oh, 5,050. So how did he do that? Well, he figured out this. And he didn't do it by induction. He saw that if you add 1 to n, that's n plus 1. And if you add 2 to n minus 1, also n plus 1. And you have, plus n minus 2 here, and n minus 1, n minus 2. If you add those two together, you got another n plus 1. And you could do that all the way till you hit the middle, which is n over 2. So you could kind of think of it as you get n plus 1 n over 2 times. And that's how he did that. He did 101, 101, like 100 plus 1 is 101, 99 plus 2 is 101, 98 plus 3 is 101, and do it all the way 50 times. That's 50 times 101, which is 5,050. OK. So the question was, what about induction? Is it kind of the best proof ever? And it's like, pick your poison. There's a bunch of different ways you can prove a thing. And I didn't write it here. There's this question mark. This is proof by induction. This is a toolkit. And math really, to me, is very much a creative field. Like it's something that you have to kind of sit down and work through and problem solve. You get all the toolkit, but you have to figure out how to use the tools and get the intuitions of like, ooh, this one feels like contradiction, or like, I think induction is the one that works here. And sometimes you could prove them multiple ways. Sometimes you could do it by contradiction, and someone else would do it by induction, and what have you. There's some intuitions you do start building, and some of those are, again, which one gets your hands on a good definition. Right? That's really one of the best things you could be looking for. We've got 8 minutes. Let me see if I can prove the fundamental theorem of arithmetic. All right. So fundamental theorem of arithmetic. So this is very fundamental. It's kind of as fundamental as you get in a class like this. And it is, let me write it out. Every natural number greater, n greater than or equal to 2 can be written as a product of primes. Almost seems so fundamental that it's not in our class, right? Like it's on the, when I drew that gradient the first day of class, and it was like some things are outside of the scope. This almost feels like one of those things. But we can prove it now that we have induction. So, OK, base case. And we'll be moving a little fast here because of time. So first off, we have n equals 2. Right? That's the smallest I said. N equals 2 is a product of primes. Well, n equals 2 is a prime. Done. 2 times, it's just 2 is a prime. Next one is inductive hypothesis. And that's going to say, let k be an n. Assume, k can be written as a product of primes. K written as product of primes. And then lastly, the inductive step. Look at k plus 1. 2 cases. Either k plus 1 is a prime if case 1 is k prime, then we're done. K is a product of primes because it's a prime by itself. Case 2, k equals m1 times m2. That is, it's not a prime. You can multiply 2 numbers to get k. Right? It's the definition of prime, which I'm alighting here, is that something's a prime if the only things that multiply to it are k in itself. So let's say it's m1 times m2. Yeah. Thank you. We are looking at k plus 1. So k plus 1 and k plus 1. Yep, great. So now we're a little stuck here. Because what we want to say is that we want to use our inductive hypothesis, right? But neither of these are k. We assumed it for k, but neither of these are k. So this is a little trick here, and this is actually called weak induction or normal induction. Most people just call it induction. A stronger induction is to say assume, let k be an n, assume p of k for all j less than or equal to k. What is this saying? It's saying if you have a bunch of dominoes and you're at the k plus 1th domino, you don't just need to assume that you don't just get the fact that the kth fell, and that gives you that. You get that all of these must have fell to get there. So the strong induction is to say, actually, let's strengthen our inductive hypothesis to say it's true not just for p of k, but for all j up to k. So we're flying through this a little bit, but I'll write out the stronger inductive hypothesis. So let's amend this with red. Strong. The strong inductive hypothesis, you assume k can be written as a product of primes. You instead assume for all j less than or equal to k, j can be written as a product of primes. So it's stronger. Instead of just k, everything up to it. We're not going to prove this here, but strong induction and weak induction are equivalent. You can show that they imply each other. And it kind of makes sense that, like, if you got to p of k, you must have knocked over all the dominoes to get there first, assuming you have a good base case. So lastly, if we have assumed that, now we know that, well, first we know m1 and m2 are going to be less than or equal, in fact, less than k plus 1. They multiply together to get k. So by inductive hypothesis implies m is equal to a product of primes. I don't know, p of l, let's say l primes, and m2 is equal to q1 through q, let's say, what's another letter? Let's do l prime. Okay. But in any case, we have k plus 1 is now equal to a bunch of primes. Great. And that concludes the proof. So the last thing I want to leave you with is it depends kind of on your personality. Some people just always start with strong induction, and you never run into any problems because you started with strong induction. I like to start with weak induction, and if I run into a problem that says, actually, let me use strong induction. So, you get to choose, again, pick your poison, but you get to choose which inductive hypothesis you use. This is just the strong inductive hypothesis. Great. And yeah, these sorts of things are fundamental proofs, really fundamental. And yeah, question there?
Yeah, why would, what
1 minute.
weak induction be better than strong induction? When would strong be better than weak?
Why would strong induction be better than weak induction? Why would weak be better than strong? We're out of time, so I'll answer that up at the front of the class. If you want to come up here, I'll answer that. Yeah, logistical question? You want to come up here? Yeah, okay.